Hello and welcome to Empowered Learning. This is the fourth video in the Radical Expression series. What we want to talk about today is how to quote unquote divide radical type of expressions where the expressions contain terms in it such as irrational numbers like square root of 2, square root of 3, so on and so forth. And so we want to recall that anytime we take the square root of a prime number, it is irrational, okay? And so these are numbers that cannot be expressed as fractions. Well, the problem comes into play when we have an expression that has square root of 2 or square root of 3 or something like that in it in the denominator of a radical expression. Since we can't express these types of numbers as fractions, there's no way for us to write them out to figure out exactly what they are. So that means we don't know how big or how small they exactly are. And the problem that comes into play is when we're trying to take a number like that and divide it, let's say any number for that matter, and divide it by an irrational number like square root of 2 or square root of 5, we don't know how much we're actually dividing up the number that's in the numerator. So conceptually speaking, we technically can't do that. Okay. Now, we know what division means, but technically, it's like taking a pie and saying, okay, I'm going to take this pie and I'm going to divide it up into square root of 5 pieces. Now, if you knew exactly what square root of 5 pieces were, you would do it. You could approximate, and it would be approximating would be about 1.732, but again, you don't know exactly how much square root of 5 is. So what we do to combat that, to at least make it look like it makes sense in the denominator, is do a technique called rationalizing the denominator. Okay. So let's go ahead and move down here. This first paragraph is basically what I was just talking about. So if we move to this first example, you see that I have 7 divided by the square root of 5, okay? And so this is sort of what I was trying to get at the beginning of the video, is that if we start off with 7 divided by square root of 5, well, how do we take 7 and divide it into square root of 5 pieces, okay? Since we can't write out square root of 5 exactly, then, there's no way for us, well, there is a way for us to express it. It's just that technically it doesn't make sense in the current form that we have it in, like this. However, to make it make sense for us mathematically, in other words, taking something and dividing it by something that we know how much it actually is, we rationalize the denominator, and that's what this part is. Essentially, what we're doing is we're going to multiply square root of 5 by the nth root that we need to in order to get a real number that is not equal to 0 in the denominator. And in this case, anytime we multiply square root of something by itself another additional time, meaning that we take square root of 5 and multiply it times itself twice, we end up getting what the we end up getting square root of 25 in this case, which will actually be 5. Okay, and so in general, what we end up having is the nth root that we need to multiply by both of them in order to get a real number. And just to make this clear here, let's say if we had cube root of 3, okay? So let's say if we had that, then what we would need to multiply the cube root of 3 in order to get a real number is something else by cube root of 3. But in this case, it would need to be 9, okay? And the reason for that is, of course, if we multiply that together, this would be cube root of 27. And of course, we know cube root of 27 is just 3, okay? So throughout the process of taking these radical expressions, whenever we see radical expressions in the denominator, we're going to be doing this technique here that's shown here and here to be able to what we call rationalize the denominator. And basically what that means is we're rewriting the expression in a way to where whenever we look at our denominator, it is a number that we can express as a fraction, meaning that we can quantify it and know exactly how much it is. Okay. All right, so let's look at the next example. So for the next example, we see we start off with 7 divided by cube root of x squared. Okay, and of course, we don't know how much cube root of x squared would be, even if we did know what x was. So here we rationalize the denominator by multiplying numerator and denominator by cube root of x. And so we need that because remember here we had cube root of 3, so we had one factor of 3. We needed to multiply this by cube root of 9, which we know 9 was 3 times 3, so those are other two factors of 3 that we needed. And so of course cube root of 27, we could just rewrite it like that, have the 3 factors of 3. So here we're saying that we already have the 2 factors of 2 factors of x. Here there's one additional 1 right there to end up making the 3 that we need whenever we multiply the denominators together. And so 3 factors of x means that we can just pull the x out. Similar to if we have 3 factors of 3 here, that means the result is 3. So we do that to rationalize the denominator. This actually makes sense. If we knew what x was, then we could plug it in, no problem. Of course, in the numerator, there's not much else that we can do other than just multiply 7 times cube root of x together. And so we end up with 7 times cube root of x divided by x as our answer. Okay. So that's sort of the intro to what we're going to be doing in this particular video. Of course, we'll have way more complicated examples as we go along. And again, I do a lot of these examples in these videos to give you a good mix of the kind of stuff that you'll see. Depending on what course you're taking, they may do simple examples, they may do some more difficult examples. So regardless of where you are on the spectrum of complexity, I'm hoping that these videos will allow you to be able to see enough of what you need to see. Okay. All right, so let's go ahead and move on here. Now, in general, when we say an expression possessing a radical in it is simplified, or put another way, to know that a radical expression is simplified, we have to have the following 3 things. We have to have the following 3 things possessed. Okay. In other words, there are 3 things that we need to look out for in order to make sure that we have this expression simplified. Okay. So the first thing, we need to have no perfect nth powers as factors of the radicand. So in other words, we can't have an expression having something like cube root of 27. Because if we do, we know that we can just simplify that to 3. So we can't have something like that. Okay. We can't have fractions inside of a radical. So in other words, if we're doing, let's say, square root of 2 divided by 5, can't have that. We need to somehow split it up like this and deal with it. And we can't have radicals in the denominator. Okay. So again, we can't have something like what we saw here. We also, and we'll see this as well, let's say if we have something like this. We can't have, let's say, 1 plus square root of 5 in the denominator. We'll have to find out a way to deal with this and get rid of that particular radical in the denominator as well. Okay. All right, so let's go ahead and get into some of the examples here. So we want to simplify the following radical expressions. For the expressions with variables, assume that all variables represent positive real numbers. So again, what this means is in the cases of whenever we see something like square root of x squared, we do not have to do this step of saying, all right, that's absolute value of x. We can just go and assume that it's x. Okay? And similarly, if we're talking about, let's say, the fourth root of, let's say, x to the fourth, kind of the same thing. We don't have to assume that that's absolute value of x. We can just assume that it's x. Okay, so that's basically what that statement means. All right, so let's move it on to this first example here. We know that we can't have square root of 5 in the denominator. So if we just rationalize the denominator by multiplying, well, forming an equivalent fraction here by multiplying numerator and denominator by square root of 5, then of course in the denominator we get square root of 25, which just equals to 5. And of course in the numerator we just write 2 times square root of 5, and that will be it. For our next example, take numerator and denominator, multiply by square root of 7. Of course, in the denominator, we'll get 7 as an answer, and in the numerator, we will get square root of 21. Since via the product rule for radical expressions, square root of 3 times square root of 7, we could multiply them both together. Since square roots have an indice of 2, and both expressions are square rooted. Okay. All right. So for example C, we look here and we see that we start off by saying, okay, let's form an equivalent fraction. And here we decide to multiply numerator and denominator by cube root of 5 squared, or cube root of 25, because here, if you notice, we have cube root of 5. In order to get rid of the cube root sign, we need 2 other factors of 5. So 5 times 5 is 25. So that's kind of what we're thinking about here. Okay. So of course, if we multiply cube root of 5 times cube root of 5 times 5, that will give us cube root of 5 cubed, which is just 5. In the numerator, of course, this gets to be a little messy. But essentially, since both of these have the same index of 3, we can take the 6 and the 5 squared and multiply them together on the inside. Okay, and so here we have 6 times 25, which ends up being 150 inside the radical, or in the place of the radicand in the numerator. Again, we would need 3 factors of the same thing in order to be able to simplify with the cube root of 150. But if you notice that cube root of 6 is just cube root of 2 times 3, and 5 squared is just 5 times 5. So we don't have 3 factors of anything in order for us to be able to pull out one factor. So that's why this is the most simple form. Okay. Moving on to the next example. Here we have cube root of 3. We need 2 other factors of 3. So this would be cube root of 3 squared. So cube root of 3 squared. So in the denominator here, this would just give us cube root of 27, which is just 3. And in the numerator, we would just have 7 times cube root of 9. And that would be the most simple answer there. And for example E, kind of see the same thing here, but now we see that we have the fraction. So this is the 4th root of 1/5. So using the quotient rule, We know that we can split this up as fourth root of 1 divided by fourth root of 5. And so, of course, fourth root of 1 is just 1. However, now I'll just go ahead and just write that here. So for the fourth root of 5, we need 3 other factors of 5 in the radicand here to be able to get rid of the fourth root sign. So that's why we multiply numerator and denominator by fourth root of 5 cubed. Okay, and so fourth root of 5 divided by fourth root of 5 cubed ends up just giving us 5. And of course, even though this is 1 here, I decided when I originally worked this to slide everything together. 1 times anything is just itself. And so now we just have fourth root of 125 in the numerator and 5 in the denominator. Okay. So see that we have those examples there. We'll go ahead and move on. All right, so same kind of thing. So here, what we're going to do is rewrite this as cube root of 7 divided by cube root of 4. And of course, 4 would be 2 times 2. So let me see if I can rewrite that. Just 2 squared. So here we have 2 factors of 2. We need another factor of 2 to get rid of the cube root sign in the denominator. So that sort of tells us how we're going to rationalize our denominator here. Of course, cube root of 2 squared times cube root of 2 is just 2. And now all we need to do in the numerator is just multiply everything together. Since 7 and 2 are prime, when we multiply them together, we just have 14. And thus, cube root of 14 is the simplest form of the numerator. For example G, we see that we have square root of x squared divided by a. Of course, we can use the quotient rule and say square root of x squared divided by square root of a. Since we don't know what a is, but we know that a is assumed to be greater than 0, then we can rationalize the denominator by just multiplying numerator and denominator by square root of a. Okay, so from that point, we know that square root of x squared is absolute value of x, but since x is assumed to be greater than 0, we can just drop the absolute value signs and just write x. Similarly, for a in the denominator, square root of a squared is absolute value of a, but again, we can drop the absolute value signs since we're assuming that a is greater than 0. And so thus our answer just ends up being x times square root of a all over a. So similarly, for example h, we take the square root of w to the 5th divided by y cubed, use the quotient rule to split it up, and then from there we notice that square root of w raised to the 5th could be rewritten as square root of w squared times w, and we know that square root of y cubed could be rewritten as square root of y squared times square root of y. Okay, and of course square root of y squared would be just absolute value of y, which just turns into y since y is assumed to be greater than 0. So that's why you see y right here. We have a situation where we have a square root of y left. So that's why we end up rationalizing the denominator at this point. Of course, for the numerator, we've taken this and split it up into 3 separate radical factors. And of course, square root of w squared is just absolute value of w. But again, we're assuming that w is greater than 0. So that would just be w here, w there. And of course, w times w is w squared. Okay, and we have a square root of w left in the numerator. So getting back to the rationalization part, we have y times square root of y, and we just need to multiply numerator and denominator by square root of y to get rid of the square root sign, and hence that's where that other y comes from. And in the numerator here, we just have w squared times square root of w times square root of y, which gives us w squared square root of wy. And of course, we see that our final answer is just w squared times square root of wy all over y squared. Okay. So for example, I will kind of do the same thing. So from here, we know that square root of a cubed is just square root of a squared times square root of a. Square root of b to the 7th, I'm going to rewrite it this way to kind of make it short. Okay. And so square root of a squared is just absolute value of a, which just ends up being a. Square root of b to the 6th could be rewritten as b to the 6 divided by 2, which just ends up being b to the 3rd times square root of b. And of course, we would rationalize the denominator by multiplying numerator and denominator by square root of b. So we'll have a times square root of ab in the numerator, and we will have b cubed times b in the denominator. And of course, our final answer will just end up being a times square root of ab divided by b raised to the 4. Okay. Okay. So for example J, we see that, go ahead and get some of these other examples here. See that we're doing the same thing here. So this would be cube root of 3 divided by 4a squared. Use the quotient rule here. We know that cube root of 3, there's not much we can do with that. However, we can take the cube root of 4a squared and break that up. Cube root of 4 times cube root of a squared. If you notice here, we have a cube root of 4, okay? So one of the things that I ended up doing here, this is just my approach, is that I said, all right, well, in order to get the 4 from under the radical here, I would have to multiply cube root of 4 by cube root of 4 squared. So that's why that's there. And same thing with cube root of a squared. I need another factor of a under the cube root sign in order to get a by itself. So that's why you see that there. So from here, we multiply both numerator and denominator by cube root of 4 squared times cube root of a. So that's why you see this in the numerator as well. So for the denominator, we just know that we're going to end up with 4 times a. In the numerator, we just have cube root of 3 times cube root of 4 times 4 times cube root of a. And so all that goes together, and we end up getting just cube root of 48a in the numerator and just 4a in the denominator. Okay. So for example K, I'm going to do the same thing. And so for our denominator here, actually I'm going to rewrite this. For the denominator, I'm going to say cube root of 2 times cube root of b squared, okay? And so here we see that we're going to need to multiply numerator and denominator by cube root of 2 squared, because we need 2 more factors of 2, as well as multiplying by cube root of b, okay? So we'll need to up here do the same thing here. And of course, in the denominator, we'll just have, if we multiply cube root of 2 times cube root of 2 times 2, we just have 2. And if we multiply cube root of b squared by cube root of b, we just end up having b. And in the numerator, of course, we don't have 3 factors of anything that's under any of these radicals, so we're just going to combine everything together. So this would be 5 times 2 squared is 4 times b. And so now we just have cube root of 20b in the numerator divided by 2b in the denominator. And so that's what our final answer would be there. For example L, we notice that square root of, we know that square root of 15 divided by 5 could be rewritten this way. So that's the first thing. And from there, we know that square root of 15 is square root of 3 times square root of 5. All that divided by square root of 5. We have the square root of 5s that reduce to 1. So our final answer ends up being square root of 3. Okay. Example M is very similar, meaning that square root of 14 divided by square root of 7 is just the same as square root of 7 times square root of 2 divided by square root of 7. The square root of 7 is reduced to 1, and we have square root of 2 as the result. So for example N, looks a little different, but the concept is the same. We need to take 5 times square root of 12. We know that square root of 12 can be rewritten as square root of 2 times square root of 6. And we divide that by 4 times square root of 6. The square root of 6 is reduced to 1. And we end up with 5 times square root of 2 all over 4. Okay. And we could go a little further with that if we wanted to. We know that square root of, the square root of 2 here, nothing, we can't do anything with that, but we can do something with square root of 4. Excuse me, I mean that not square root of 4, but just 4. So we know that 4 can be rewritten in square root form as square root of 16, okay, which is square root of 2 times square root of 8. However, if you notice here, we would probably take the square root 2's here and reduce them to 1, but that would end up in us having a square root of 8 in the denominator, which is what we don't want, that, because then that puts us back into a situation where we have to rationalize the denominator. So all that to say that even though we know that there's some commonality here in between the square root of 2 and the 4, we have met the criteria to have a radical expression in most simple form. So this would be our answer for that. This would be an acceptable answer, I should say. All right, so let's get rid of some of this other stuff here. And then we'll move on. All right, so for example O, we see this one is a little bit more involved, but pretty much the same concept. All right, so we have the fourth root of 81b raised to the 5 divided by the fourth root of b. So when we rewrite that, we see in the numerator we have the fourth root of 81, and 81 is just 3 raised to the fourth power, so that's a perfect fourth root. We also see that we have the fourth root of b squared, and b to the fifth, and b to the fifth could be rewritten as b to the 4 times b, and so we see that simplifies to just b times fourth root of b. And so with the fourth root of b's here being both in the numerator and denominator, we see that they end up reducing to 1. And all we have left is 3b as our answer. Okay. So the examples that we've seen, of course, are ones where we've had some expression that is in the denominator that ends up having to have us rationalize it. But in most of these cases, we've just had an expression in the denominator that's one term. What we're going to deal with next is expressions in the denominator that have 2 or more terms, and we're going to see how we actually go about rationalizing the denominator in that case. All right, so looking at our next example here, what we're asked to do in this case is to write the expression 3 divided by square root of 11 minus square root of 5 in a simplified form. Now, if you recall, we are not allowed to have any radical expressions in the denominator at all. So this square root of 11 minus square root of 5, we can't have that. Now, if you recall, one of the things that we know is that if we had an expression, let's say a minus b, and we multiplied it times an expression a plus b, we end up getting a squared minus b squared. And if both of these expressions are what we call irrational conjugates of each other, then this ends up actually being a real number. Okay. Now, saying all that to say is that essentially what we need to do here is multiply numerator and denominator by the conjugate of what the denominator is. And of course, the conjugate of the denominator is square root of 11 plus square root of 5. Okay. Now, to multiply the denominator together, we just use this formula here and just say, all right, well, that's square root of 11 squared. And this will be minus square root of 5 squared. Okay. And when we work that out, square root of 11 squared is just 11. Square root of 5 squared is just 5. For the numerator, all we're doing is taking the 3 and multiplying it by both terms there. So to keep it simple, we could just say this. Okay, and we could really just leave it like that, and that'll be fine. So if we come here, square root of 11 plus square root of 5, and so here we know that the denominator is just 6, and we could simply leave the answer like that. And then for this last part, we can just reduce the 3 and the 6 to 1 over 2. So let's reduce, and we just have square root of 11 plus square root of 5, all that divided by 2. So that will be our final answer there. Okay. Using a similar technique here, we know that the conjugate of square root of 7 minus square root of 5 is just square root of 7 plus square root of 5. So we'll kind of do the same thing here. So this will be square root of 7 plus square root of 5 divided by square root of 7 plus square root of 5. This will be 5 times square root of 7 plus square root of 5, all that over square root of 7 squared minus square root of 5 squared. Okay, and of course square root of 7 squared, that is just equal to 7. Square root of 5 squared, that is just equal to 5. And 7 minus 5 is 2. And so for the numerator, we just have 5 times square root of 7 plus square root of 5. And that is what our final answer ends up being. So moving on, we want to simplify the following radical expressions raised to some power. So examples A and D sort of give us an idea of what we're looking for here. So I'll do that and then work examples B and C. So we have 3 times square root of 3, all that raised to the 4th power. So if we use the exponential rule of saying the product of any two things raised to a common power, we can rewrite it as each factor raised to that same power and then multiply the result. Then we see that we have 3 raised to the 4 times 3 raised to the 4 times square root of 3 raised to the 4. Okay, and of course 3 raised to the 4 is just 81. Here we have, we could rewrite square root of 3 raised to the 4th as just square root of 3 raised to the 4. Okay, and I rewrote this way, but I'm going to change this. Here we know that 3 raised to the 4th is 81, so we could think of this as square root of 81. And square root of 81 is just 9, so that's how I get the 9 here. When I originally worked this out, I thought of everything in terms of, since this is an index of 2, I know that I need 2 factors of something to be able to pull it out. And of course, 3 squared is 9, so I need 2 factors of 3 squared to get 3 squared, which is the same thing as 9. So at the time I was working this, that's kind of what came to mind, so I did it. But simply, we could just say 81 times square root of 81 and then just jump directly to here. And then, of course, our final answer is 729. In example D, same thing. We can do take each factor and cube it. So we have 2 cubed times y cubed times cube root of 4y cubed. Okay? And of course, 2 cubed is 8. Y cubed is just y cubed. And we're for this last factor, we're undoing the cube root, so we just end up with 4y. And of course, our answer is just 32y raised to the 4th. Okay, since we got a y cubed here times another y. All right, so taking those examples A and D and applying it to B and C, we see that 2 times square root of 2 to the 5th can be rewritten as 2 raised to the 5th times square root of 2 raised to the 5th. And of course, 2 raised to the 5th is just 32. We can take square root of 2 and rewrite it as square root of 2 raised to the 5th, which is just square root of 32. And we know square root of 32 is the same as square root of 2 times square root of 16. Square root of 16 is 4. So what we end up with as an answer here, let me get rid of that, is just 32 times 4, which ends up being 128 times square root of 2. So we'll just have 128. These two things multiply together times square root of 2. And that will be our final answer. Okay. For example C, let me clear this out so we'll have a little more room. All right, so for example C, we're going to do the same thing. So we'll take our -2, cube that. We'll take x and cube that. And then we'll take the cube root of x squared and cube that. And so -2 cubed is just -8. X cubed is just x cubed. And then the cube root of x squared cubed, we're just undoing the cube root. So that's just x squared. And then from there, we can multiply x cubed and x squared to be x to the 5th. And this is what our final answer ends up being. Okay.